Okay, I think we can start now. Okay, yeah, thank you everyone for attending and welcome to one more lecture of our Processing in Memory course. Today, we are going to talk about the benchmarking and workload suitability on a real-world processing in memory architecture. And this real-world processing in memory architecture is the PIM architecture, which is familiar to everyone attending these lectures because we have talked about it in several of the previous lectures. As you may remember, it's composed by DRAM, DIMMs, including several chips. And in these chips, we find different memory banks. As you can see, 64 DRAM banks called NRAM, and then attached to each of the banks, we have a DPU or DRAM processing unit. The DPU is composed by a pipeline of 14 stages, and then two SRAM-based memories. One is for instructions, and the other one is for operands. Remember as well that the PIM system follows the accelerator model. What this means is that we need to explicitly move data between the main memory of the CPU of the host and the memory of the accelerator, in this case, the DPUs. And after we have moved the input data, we can launch the computation and start the processing on the DRAM processors, on the DRAM processing units. And then the CPU keeps checking until the computation is done on the memory side, and then the memory banks become accessible to the host processor. Last week, in our previous in our last lecture, we were talking about we had our first discussion and our first lecture about processing in memory programming. We talked about one example, initial example, which is a vector addition. Remember that in vector addition, if we want to implement this on an PIM-based PIM system, what we will do is dividing the whole computation into different chunks, each of them assigned to the different DPUs available in the system. For example, here, if we have 4 DPUs, we will able partition the arrays and assign them to the DPUs, and then inside the DPUs, we will use tasklets that are the software threads that run on the DPU to compute the individual element-wise additions that we have in this case, for example, in vector addition. Remember that we discussed or we talked about some general programming recommendations. The first of them, 4 general programming recommendations in particular, the first of them is to execute on the DRAM processing units portions of parallel code that are as long as possible. And there are a couple of important reasons for this. The first one is to make sure that we are parallelizing more, and based on Amdahl's law, we can achieve higher performance improvement in the overall execution of the application. And the second reason is that if these portions of parallel code are longer, we will be less bound by the overhead of communicating between the main memory of the CPU and the NRAM banks. The second general programming recommendation is to split the workload into independent data blocks so that the DPUs can operate independently on them. The idea here is that if these independent data blocks, same as we have just seen in vector addition, if the computation on each DPU is independent on whatever is happening on another DPU, we won't need to communicate across DPUs, because the problem we have is that all inter-DPU communication must happen through the host CPU by using CPU-DPU and DPU-CPU transfers, as you may remember from our previous lecture. So if we want to minimize this overhead of the inter-DPU communication, it's better to try to assign completely independent tasks to the different DPUs as much as possible. The third programming recommendation is to use as many working DPUs in the system as possible as well. Of course, if our data set is large enough, we will be able to use all DPUs available in the system. If not, it might be better to use a smaller number of DPUs, especially in cases where we need to synchronize across DPUs, because in this case, and actually something that we are going to discuss today as well, if we have multiple DPUs, we will incur more cost from the synchronization and communication across DPUs. But in principle, in order to exploit as much parallelism as possible, it's better to use as many working DPUs as possible. And the fourth programming recommendation was to launch at least 11 tasklets or software threads per DPU. And the reason for that is something that we also discussed in the previous lecture, but also when we were presenting the microarchitecture of the UPMEM-based PIM system, the UPMEM DPUs, and we were micro-benchmarking these DPUs, and we observed that the arithmetic throughput, the throughput of the arithmetic pipeline saturates at 11 tasklets. And this is the main reason why 11 tasklets at least seems a good number of tasklets or software threads executed on each DPU. Remember as well that CPU, DPU, and DPU CPU transfers happen through the host CPU. This is what we call a CPUGPU transfer, when we copy data from the main memory to the PIM-enabled memory or the UPMEM DIMMs, and this is a DPU CPU transfer. Remember as well that there are three different types of transfers. Serial transfers, either CPU, DPU, or DPU, CPU. In this case, we target a single DPU or a single MRAM bank. So this means that if we issue multiple serial transfers to multiple DPUs, these all will be serialized. So the time needed for the transfer time will increase. But we can also use parallel CPU, DPU, and DPU, CPU transfers when we are targeting multiple DPUs. And these parallel transfers, we can use them when the size of the buffers that we are going to transfer from the main memory to the PIM-enabled memory, or vice versa, are of the same size. Then the third type of transfer is like a special case of the parallel CPU-DPU transfer. It's the broadcast transfer. In this case, we are transferring multiple DPUs. So we are transferring two multiple DPUs, but we transfer a single buffer. Remember as well how important was to understand how costly and what's the bandwidth that we can achieve in this CPU, DPU, and DPU, CPU communication and transfers, because they are the way of communicating across DPUs, because there is no direct communication channel between DPUs, right? So, and remember as well that we talk about some possible example communication patterns. One is the merging of partial results to obtain a final result. Another one is the redistribution of intermediate results for further computation. Today, we are actually going to talk about some of the codes that we have implemented to do our benchmark analysis and workload suitability analysis on the UPMEM architecture, and we will see some of these patterns. After talking about the vector addition, we went for a little bit more complex code, in this case, the parallel reduction, that requires some communication inside the DPU, communication across tasklets, because the way that we implement parallel reduction is by dividing the whole input that we need to reuse among the different available tasklets, and then in the reduction, what each of the tasklets do is calculating a local sum, and at some point we will need to reduce these partial local sums into a final sum per DPU. And the way to do this final reduction might, I mean, we can do it in different ways. We actually talk about three potential ways of doing it. The first way would be to have a single tasklet reducing all these values. The other two ways are based on a tree-based reduction. One of them is an implementation using barriers, and another way of implementing this tree-based reduction is by using handshakes. In the end, what we have observed is that the best performance in the current UPMEM-based PIM system is obtained by the single thread execution, but it's mainly because of the fact that the number of tasklets that we are using is not too high. It's, for example, a number like around 8 or 16 in the end, related to the maximum number of hardware threads that we have in the system, and because we don't really need to reduce so many values. Let's say only 16, a single thread is already pretty efficient in this case. Okay, so this is just like a very brief summary about what we discussed in the previous lecture. Please let me know if you have any questions. As usual, I will keep checking the YouTube chat from time to time in case that there are questions there as well. Okay, so today, as I said in the beginning, we are going to talk about benchmarking and workload suitability. In the end, what we try here is to identify what are the key characteristics of real-world workloads or real-world execution patterns that can benefit from processing in memory architecture like PIM. So in order to do so, what we did was developing a benchmark suite that we call PIM, and codes that belong to this benchmark suite have been carefully selected based on their diversity and based on the different environment, different fields that they belong to. So that's the first thing that I want to discuss with you is about this benchmark diversity of the PIM benchmark suite. So it's a common set of workloads that is developed with the intention of evaluating the PIM architecture, but also compare software improvements and compiler, or compare future PIM architectures and hardware. In the end, these are like the typical reasons why we want to develop a benchmark suite, not only for this architecture, but also for other architectures as well. Evaluating the architectures and then using the benchmarks to evaluate as well possible software or hardware and architecture improvements. There are two key selection criteria when we decided to select what are the benchmarks that we want to implement on this architecture. The first one is use workloads that belong to different application domains, as we will see in the next slide, and also workloads that are potentially suitable for processing in memory. And those workloads that are potentially suitable for processing in memory, as we already know, are from previous lectures as well, are workloads that are clearly memory bound on processor-centric architectures like CPUs or GPUs. In total, the PIM benchmark suite contains 14 different workloads and 16 different benchmarks, because as you will see, we have two versions of two of the workloads. And this is the list of benchmarks. As I said, you can find here different domains like sparse and linear algebra, databases, data analytics, graph processing, neural networks, and so on. And as I said as well, there are two workloads that have two benchmarks. One of them is image histogram. Depending on what's the size of the histogram, we will prefer to use one implementation or the other one. And then we also have two different versions of the prefix sum primitive. So the first thing that I want to show you is that these benchmarks are memory bound in a processor-centric system, as I said. So in order to do so, we use the roofline model. As you probably know, the roofline model represents the performance in operations per second with respect to the arithmetic intensity in operations per byte accessed from memory. Right, so and here we essentially have two roofs. One is the roof defined by the memory bandwidth, in this case the DRAM bandwidth. So for those workloads that have a low arithmetic intensity, it's going to be kind of the maximum throughput that you can achieve, unless you can fit at least part of the data set in the cache hierarchy, and in this case we may be able to go beyond this line. But in the end, as long as we have a workload that is on the left side of this say elbow of the roof line, we can talk about memory bound workloads, and the other roof of the roofline model is the peak compute throughput that is given by the available execution units that we have in the processor, right? So these are some of the these are the 14 workloads, and as you can see, all of them fall in the memory bound area of the roofline. So the second reason to select these workloads is that they are diverse, and they are diverse in terms of memory access patterns. As you can see, some of them have sequential accesses, strided accesses, random accesses. Remember that when we talk about the binary benchmarking of the architecture, we were also studying what was the bandwidth that we could achieve from memory for these different memory access patterns. We also have different computation patterns in terms of operations that are used and data types as well. And we also have different communication and synchronization needs. In some of the workloads, we need to have intra-DPU communication, and this happens across tasklets running on the same DPU. And for those, we use handshakes, barriers, mutexes that we presented in the previous lecture. And then also in some of the benchmarks as well, we need to do inter-DPU communication. And this inter-DPU communication might be, as I said before, two different ways of the inter-DPU communication. In some cases, we will see that it's pretty simple. It's just unidirectional. It's only a result merging, for example, in these histogram benchmarks. If we are generating a histogram, a subhistogram or a partial histogram in each of the DPUs, in the end, we want to gather all these histograms or these subhistograms, bring them to the CPU, and we will perform the final reduction of these partial subhistograms in the CPU, right? So in this case, the inter-DPU communication or synchronization needs are only unidirectional in the sense that it's only like merging the final results or the partial results that we obtain in the DPUs in order to obtain the final result on the CPU. And in other cases, we have more complex communication patterns that require redistribution of intermediate results. And I think that a good example here is, well, any of this is a good example, but for example, BFS is a graph processing algorithm. Graph processing is that algorithms are typically iterative, and the implementation, you can, by the way, find details about the implementation of all these algorithms in our paper that is available in arXiv. But in this case for BFS, we implemented a top-down approach. In the top-down approach, after each iteration, the DPUs in this case have created a frontier, so an intermediate frontier that needs to be redistributed over the available workers, available DPUs or tasklets. So what this means is that after each iteration, each of the DPUs has a partial frontier. We bring all these partial frontiers to the host CPU, we concatenate them, and then we redistribute. We assign this merge or concatenated frontier is again the input to the next iteration. So we redistribute to the DPUs for the execution of the next iteration. So this is why this communication pattern is more complex, because it requires first bringing the partial frontiers from the DPUs to the CPU, and then performing the redistribution, moving the frontier again to the different DPUs. Okay, guys, feel free to stop me if you have any questions. So after having presented the benchmarks, these 16 benchmarks that compose the PRIM benchmark suite, we are going to evaluate them. And first of all, I would like to give you this evaluation methodology that we have used. You might remember that we had access to two admin-based PIM systems. One of them is larger one. It has 2,556 DPUs. The other one has 640 DPUs. And we have run the 16 PRIM benchmarks on the two systems. We have characterized the execution of these benchmarks on the two systems by using both strong and weak scaling experiments. I mean, we have used, we have actually run these experiments on the larger system because we have more DPUs, so we can observe more scaling characteristics. I would like to recall you that the strong scaling refers to how the execution time of a program solving a particular problem varies with the number of processors for a fixed problem. So in this case, we have a fixed problem size, and we distribute the workload, the computation among the available DPUs. If we increase the number of DPUs, the amount of computation per DPU will be lower, right? So that's a strong scaling. And in the weak scaling experiments, what we do is increasing the size of the problem as we increase the number of processors. So in this case, we assign a certain amount of computation to each DPU. And as we start using more DPUs in the system, we will have a bigger problem to solve by these DPUs. So this is essentially the difference between a strong and weak scaling experiments. So we run these experiments on one DPU for different number of tasklets. So these are strong scaling experiments that we run here on a single DPU. For one rank that is 64 DPUs, we run both strong and weak scaling experiments. And then again, for strong scaling experiments, we used up to 32 ranks, which are 2048 DPUs. Also, as a part of this evaluation and evaluation of the benchmarks and this discussion about workload suitability, we compared the execution of the benchmarks on the AppMem-based PIM systems to the execution of the benchmarks of their CPU and GPU counterpart implementations onto real state-of-the-art CPUs and GPUs. And we use some data sets that are also accessible in our repository for the strong and weak scaling experiments. And here you have, like the whole list of data sets for strong scaling. These are the data sets for one DPU or one rank. These are the data sets for 32 ranks, and then weak scaling data set. And also for reproducibility of our experiments, you also have here the MRAM, WRAM transfer sizes, the DMA transfer sizes that we use or can use or need to use to move the data from the MRAM to the WRAM and vice versa. And yeah, if you want to take a look at the benchmarks and also the data sets and the scripts that we used in our experiments, they are all available in our repository. So let's start discussing the results for strong scaling on one DPU. The idea of this experiment is to essentially see what's the best performing number of tasklets. Remember that one of the key programming or general programming recommendations was to use at least 11 tasklets. And now we want to see if this is it's a good programming recommendation or not. Hopefully it will be. So as you can see on these different plots for the 16 benchmarks, we set the number of tasklets to 1, 2, 4, 8, and 16. And in each of the plots, we show the breakdown of execution time for the DPU kernel time, which is essentially the execution of the kernel, the function that runs on the DPU. And we see here, for example, for vector addition, how this execution time, how this DPU kernel time reduces as we increase the number of tasklets as we desire and could expect as well. There is also, in some of the benchmarks, you will see that there is also some amount of inter-DPU communication. As I said before, this might be because we need to redistribute intermediate results, or maybe because we need to merge the final results on the host CPU. We also have the time for the CPU to DPU transfers of the input data and the DPU to CPU transfers for the final results. And finally, we can also see the speed up of the DPU kernel time with respect to a single tasklet. So as we increase the number of tasklets on the DPU, we should also expect that this speed up will increase. So yeah, let's start discussing these results in more detail. So as you can see, okay, I don't know if there is something wrong. No, it seems it's okay. So as you can see, in most of the workloads, actually, the best performing number of tasklets is 16. In all these workloads that are highlighted on the screen right now, you can see that in all of them, the best performing execution time or the lowest execution time happens when we are using the maximum number of tasks that we are running in the experiment, which is 16. And this is something that makes sense because remember, the general programming recommendation is to use at least 11 tasklets. So in this case, we are using 16 and we are obtaining the best performance in most of the benchmarks. One interesting observation here with respect to these benchmarks, these 13 benchmarks that we highlight on the screen, is that the speed up, when we double the number of tasklets from 1 to 8, it's essentially twice. So it's and this is reasonable as well, because we are using more tasklets on the pipeline, so we are making better use of the resources, better use of the pipeline, and what this means is that we are essentially doubling the number of workers, and by doubling the number of workers, we should expect a reduction by half in the execution time of the kernel. But it's also true that we normally observe that when we move from 8 to 16 tasklets, in this case, we are not doubling the performance. And why is that? Because the throughput saturates at 11 tasklets. So we know that the arithmetic throughput saturates at 11 tasklets. So that's why we cannot expect the same speed up. We cannot expect that the execution time will be reduced by half from 8 to 16, only because the saturation point happens before 16 tasklets. So key observation here is that the number of tasklets greater than 11 is a good choice for most real-world workloads, in particular for 16 kernels out of 19 kernels from the 16 benchmarks. And observe that we have 19 kernels because in some of the benchmarks, actually these 3 benchmarks, we have 2 kernels in each of them. So that's why we talk about 19 kernels here. Okay, so other observation is that some of the workloads, these ones highlighted on the screen, don't use intra-DPU synchronization primitives. So because they don't use intra-DPU synchronization primitives, we don't have tasklets having to wait for other tasklets to complete their some task or certain operations, right? We don't have a barrier, for example, where the first tasklet that arrives has to wait until all tasklets arrive at that point before continuing the execution. So this definitely favors scaling, and in these benchmarks where we don't see any sort of intra-DPU synchronization is where we can see the best scaling inside the same DPU, when we increase the number of tasklets. In some other workloads, this intra-DPU synchronization exists. For example, in the reduction, remember that in the parallel reduction, in all cases, in all 3 implementations, actually, we need to synchronize the tasklets after they have computed their own local sum, and to do so, we use a barrier, but this barrier in the end doesn't represent so much overhead, so we still see good scaling from 8, so when we increase the number of tasklets. And then there are also 3 of the benchmarks where we have quite a bit of contention when accessing shared data structures. And the way of accessing these shared data structures is by using mutexes. So remember that a mutex creates or defines a critical section where only one of the tasklets can be working at a time. So every time that we have a tasklet executing the critical section, if another tasklet arrives at the mutex, it cannot acquire the lock. It will have to wait for the tasklet executing the critical section to release the lock before the next tasklet can go inside the critical section. And yeah, let me give you a particular example. In this case, one of the versions of histogram. This is called HSTL, L coming from long, because this version is more suitable for longer histograms. And so the difference with respect to the other version of the histogram, the HSTS, that is S from short, is that that short version can use, so it's only for relatively small histograms in a way that each of the different tasklets can have its own subhistogram in the WRAM. And and after all these partial subhistograms in WRAM are created, the tasklets will reduce them into a final subhistogram per DPU, and after that transfer these partial subhistograms per DPU to the host for the final reduction. In the case of the long version of the histogram, the histograms are expected to be longer. So what that means is that we cannot allocate as many histograms as tasklets, right? So in this particular case, we are using a single subhistogram for the whole DPU. And if we have more than one tasklet creating this subhistogram, because in the end, a histogram is an operation that requires us to update certain counters, and these could cause data races. Because we want to avoid these data races, we need to use mutexes when going to access the histogram. So what this essentially means is that each of the tasklets goes to memory, reads the input values. These input values have, these input elements have certain values. Depending on the value of the input element, we go to the corresponding element or bin of the histogram, we update it, and then we continue the execution. So these updates need to be saved. We should avoid data races here, and the way to do it is by using mutexes to define a critical section, which in the end here is the update of the subhistogram, right? So, so what happens is that when we start increasing the number of tasklets, because we are making a better use of the resources, and we are better use of the pipeline stages, we are exploiting this parallelism with the multiple tasklets. We see that the execution time reduces, but at some point it increases again. And the reason for that is the contention that we have when accessing the mutex. The more tasklets we are executing on the DPU, the more tasklets will have to wait for other tasklets to complete the critical section before they can go and update the histogram. And this is the reason essentially why for this HSTL, we obtain the best performance for 8 tasklets instead of 16. So as you see here, in this particular case, the best performing number of tasklets is not 11 or larger, right? So in this case, it's 8. Okay, so one more interesting observation here in the strong scaling experiments for one DPU. We have so in this benchmark in particular, this version of the scan or prefix sum benchmark, we also see that the best performing number of tasklets is not 16. In this case, 16 and 8 have essentially the same performance, right? And the reason for this is that the scan SSA kernel is not compute intensive. It's not compute intensive because this is just a single addition. So here in this in this scan add kernel, the only thing that we are doing is reading elements from an array that resides in the MRAM, and we are adding a certain constant value to each of the elements in the array. So in the end, we are reading elements from memory, just performing one addition per element, and then we write back. So it's not really a compute intensive kernel, because the amount of computation is very small. It's just a single addition. And because it's not compute intensive, we are on the memory bound area. As you may remember, when we did the micro benchmarking, we discussed the micro benchmarking, we are in the memory bound area of the roofline of the analysis of the arithmetic throughput with respect to the operational intensity. So the operational intensity is quite low. So the component that limits the performance of this benchmark, of this workload, this particular kernel, sorry, is the access to main memory, not the execution of instructions in the pipeline. And even though this doesn't happen in many of the workloads, essentially in all other kernels, we can say that they are in the compute bound region, but this is a special case that resides in the memory bound region. But other than this one, most of the kernels and most of the workloads that we have tested are in the compute bound region. So it's reasonable to expect that the best performing number of tasklets will be 11 or more, unless we have intra-DPU synchronization primitives that may create some contention and might reduce the performance for number of tasklets larger than 11. Okay, one other observation for these strong scaling experiments on a single DPU, we have this TRNS, meaning transpose. Here, essentially, what we do is a matrix transposition, and one thing that we observe in this matrix transposition is that the CPU to DPU transfer time is like very high, right, as compared to other parts of the execution, like even the execution of kernels like this. Step 2, which is the lighter blue, or this step 3, which is the darker blue. So the reason for this to be so long is that this is this is not simply transferring a buffer from the main memory to the MRAM banks. Here, what we are doing is executing the first step of the transposition algorithm. I'm not going to go into the details of this transposition algorithm, but this is a 3-stage transposition in an architecture where we have a shared memory. We would execute this step 1 in the processing units, in the execution units, but in this particular upman-based PIM system, because this is kind of a distributed architecture, we need to execute this step 1 by moving pieces of data or chunks of the input matrix to the specific DPUs that are going to continue the later steps, the steps 2 and 3, right? And for these transfers, we are using relatively small transfers, only 8 elements of the matrix, and in this case, we are not fully exploiting the CPU-DPU bandwidth. As you may remember from the previous lecture, the CPU-DPU bandwidth and the DPU-CPU bandwidth increases with the size of the transfer until some point when it saturates, but 8 elements is quite a small number of tasks, quite a small number of elements, a small transfer size, so we cannot fully exploit this bandwidth on the memory channel. So this is why we see these large CPU-DPU transfers for this step 1, as I said. So an observation here is that as long as possible, we should use large transfers from the CPU to the DPUs or vice versa, because this way we can exploit the higher sustained bandwidth, as we also saw in the previous lecture. Okay, so after having discussed the results for strong scaling experiments on a single DPU, let's talk about the strong scaling experiments on one rank. One rank meaning a number of DPUs between 1 and 64. So now we actually run experiments on 1, 4, 16, and 64 DPUs, all of them inside the same rank. And in each of the experiments, in each of the DPUs, we are using the best performing number of tasklets that we have obtained with the previous experiments. And now if you take a look at the breakdown of execution time, again, you have the DPU kernel time. Here you have some inter-DPU synchronization time. It will be more frequent in these experiments for sure, because we are using more than one DPU. We also have CPU-DPU transfer time and DPU-CPU transfer time, and finally the speedup. In this case, the speedup is over a single DPU, right? Okay, so let's start discussing some of the results. So the first thing that we observe is that in most of the benchmarks, except 2, we see that there is a linear scaling with the number of DPUs. And what this means is that as we increase the number of DPUs, we achieve a speed up that is in the order of magnitude of the number of DPUs that we are using. For example, here for Gen V, you see that when we go from 1 DPUs to 64 DPUs, we are essentially obtaining 60 times or even more speed up, right? It's something that looks pretty nice, this linear scaling for all these benchmarks. But we see that the scaling is sublinear for BFS and for NW, for Needleman Bunch. But the main reason, I mean, there are different reasons for that. In the case of BFS, the reason is that there is quite a bit of load imbalance across DPUs due to the irregular graph topology. So you know that real-world graphs are usually irregular. And there are, for example, if you think about the YouTube graph or Facebook graph, you will see that in some cases there will be users that have many connections, while other users have other users have only very few connections, right? And what this means is that the graph is irregular because some of the vertices or nodes of the graph will have many neighbors, while others will have only a few neighbors or maybe only one, right? So this irregular graph topology creates a load imbalance across the tasklets and across the DPUs. So that's the main reason for this sublinear scaling in BFS. And in the case of NW, the reason is related to the way that the NW operates. NW operates on the diagonals of that two-dimensional matrix. And if you think about the diagonals, they all have a different length, right? So depending on the diagonal, the particular diagonal, you will be using, or you would need to use more DPUs or less DPUs. So even if we allocate more DPUs, even if we allocate 64 DPUs, or even if we allocate 2000 DPUs, we will use as many DPUs we really need for the length of the diagonal that we are processing in each iteration. And only in the longer diagonals, those in the center of the matrix, we will use probably all DPUs, and in those cases, we will achieve linear speed up. But for the overall execution, all iterations on the multiple diagonals, because we are not using all DPUs in the shorter diagonals, this is why we see this sublinear scaling. Okay, so now a few comments with respect to the inter-DPU synchronization. So we see that there are some benchmarks that don't need inter-DPU synchronization at all, which is great for their performance and for the execution on this distributed system, in particular these 6 benchmarks that you see on the screen. Then there are also other benchmarks, these ones with the orange halo or orange apron that require inter-DPU synchronization, but still 64 DPUs obtains the best performance. And in this case, when I talk about the performance, I mean the added execution time, including or the overall execution time, including DPU time, DPU kernel time, and inter-DPU synchronization. So the good thing in these 7 benchmarks is that the inter-DPU synchronization is pretty lightweight. So yeah, as I said, still the best performance is obtained with the maximum number of DPUs. And then there are 3 benchmarks that are much heavier in terms of inter-DPU synchronization, essentially because these 3 require DPU, CPU, and CPU GPU transfers for the execution of the algorithm. So iteration after iteration, we need to move data from the MRAM banks to the host CPU, then rearrange these intermediate results in some way and redistribute again onto the DPUs. And this is why this inter-DPU synchronization is quite costly for these 3 benchmarks. And if we observe, for example, here, BFS, we compared the execution time of 16 DPUs, including the inter-DPU synchronization. We compare it to 64 DPUs. We see that yeah, it's essentially the same. Perhaps 64 is still a little bit lower, but yeah, for sure, far from what we could expect from using 4 times more DPUs. And something similar happens as well with NW and MLP as well. Okay, yeah, so in some of the benchmarks, I mean, in a majority of benchmarks, as you can see, we can use parallel transfers between CPU and DPU and between DPU and CPU. So this means that the execution, so the time needed for these parallel transfers decreases as we increase the number of DPUs. And why is that? Because we are inside the same rank, and inside the same rank, we can parallelize the transfers. We can achieve higher bandwidth as we increase the number of DPUs. This is something that we discussed in the previous lecture, and that's what we observe for these benchmarks. In other cases, we cannot, so we can use parallel transfers, but we don't see a reduction in the transfer time. It's the case of BS and NW, but the reason is essentially for BS, the reason is that we are transferring the complete array, the complete input to all DPUs in this experiment. So we are not really partitioning partitioning one of the input arrays. It's not the only input array in BS, it's binary search. So what we have in this workload is an input array, a long input array, and then we have a series of values that we want to find in this input array. And the way that we distributed the computation here is by distributing the input values that we want to search in the input array across the multiple DPUs. But still, the array is the same for all the DPUs, the array where we look for the values. So in the end, if we increase the number of DPUs, we are also increasing the amount of data that we transfer to the different DPUs. And for NW, one reason to see, you know, that the transfer size does not reduce when increasing the number of DPUs is because, for the same reason that we gave before for Needleman-Bunch, we are not using all DPUs in all iterations of this NW benchmark. So what that means is that we are not increasing the sustained bandwidth while increasing the number of DPUs, because we are not using all DPUs all the time. And actually, in most of the cases, we are only using, in most of the diagonals, we are only using a reduced number of DPUs. Okay, then we have these 4 benchmark SPMB, Select, Unique, and BFS that cannot use parallel transfers, or at least in one of the directions cannot use parallel transfers. Let me give you the example of Select. We actually talked about Select in our previous lecture. We said here in Select, you have an input array and you want to filter some of the elements, get rid of some of the elements, for example, those that have an odd value. And when it comes to moving the input array from the CPU memory to the DPUs, we can equally partition or evenly partition the input array and have buffers of the same size and perform parallel transfers. But then, depending on the actual values on the input array, we will have more or less values, elements to transfer in the opposite direction from the DPUs to the CPUs, right? That will depend on the values in the input array. So that's why we cannot use parallel transfers in the retrieve transfer, in the DPU to CPU transfer. And this is why we see, look at these DPU CPU transfer times in Select, that they increase as we increase the number of DPUs, because we are not parallelizing them. So one programming recommendation here is that for parallel CPU, DPU, and DPU CPU transfers inside a rank of DPUs, and we recommend to use parallel transfers inside a rank of DPUs when the transfer buffers are of the same size. So this is let's say, obvious programming recommendation that we could expect and we could have given last week after observing the sustained bandwidth for parallel and serial transfers and broadcast transfers and so on. But here you can see the actual effect of the parallel transfers or the serial transfers for the different benchmarks. Okay, now we move to the next set of experiments. These are strong scaling experiments on 32 banks. In this case, 32 ranks in this case, or up to 32 ranks. In this case, we use a number of DPUs between 256 and 2048, and we show the execution time execution time breakdown again. This is again the DPU kernel time and the inter-DPU time. Here we are not showing CPU, DPU, or DPU, CPU transfers. And this speed up line corresponds to the speed up over 256 DPUs. So if we are multiplying the number of DPUs by 8, as we are doing from 256 to 2048, we could like to expect a speed up of around 8, right? To show like nice linear scaling. And that's actually what happens in most of the workloads. As you can see, they scale linearly with the number of DPUs. In others, there is no linear scaling due to load imbalance, each of them with its own characteristics and particularities, but these three benchmarks don't scale so well. So key observation here is that load balancing across DPUs ensures linear reduction of the execution time spent on the DPUs. So as long as possible, if we are able to achieve load balancing, as we have obtained in these in 13 of the 16 benchmarks, it's better to use the largest possible number of DPUs, and we can expect linear scaling. So one more, some more observations here is some of the benchmarks don't meet any sort of merging of final results. These particular 5 benchmarks, they only need to merge final results. So the overhead of merging these final results is tolerable. Good thing here is that we only need, so when merging the final results, we only need to do DPU to CPU transfers. There is not much inter-DPU communication, and the cost, the overhead of this merging of partial results on the host CPU is tolerable. When I talk here, by the way, about inter-DPU synchronization, it's not only the data movement over the memory bus, it's also the possible computation that we need to do on the host system. So for example, if we are calculating the final reduction for the reduction kernel or the final histogram for the histogram benchmarks, we are obviously not only including in this inter-DPU communication, not only the data transfer itself, but also the computation on the host CPU for the final reduction or the final merging. There are some other workloads, as you know, that require more complex communication because they need to move first the data intermediate results from the DPUs to the CPUs, and then rearrange and then moving back to the DPUs. So in those cases, the inter-DPU synchronization is much more noticeable, and it imposes a significant overhead, especially in some of these benchmarks like BFS, NW, and MLP. And here we see that this inter-DPU synchronization time is huge because also the number of DPUs that we are using is huge. If you compare these results on 32 ranks with the results on 1 rank, you will see that in those, the weight of the inter-DPU synchronization with respect to the DPU kernel time itself is not that high. And we also have experiments, as I said in the beginning, weak scaling experiments on 1 rank in this case. What we can observe in most of the benchmarks is that the scaling is perfectly linear. You can see, for example, this TS here, or the 2 versions of histogram, where we see that the execution time is completely flat. Remember that in weak scaling experiments, we increase the size of the problem as we increase the number of DPUs in the system. So in most of the benchmarks where they are equally sized problems assigned to different DPUs, and in these benchmarks as well, where we don't have so much inter-DPU synchronization, we see linear weak scaling. And vector addition is one example. You can see how the DPU kernel time is completely flat as we increase the number of DPUs in the system. We also see that even though the total size of data that we are transferring increases with the number of DPUs as well, we see that there is not so much increase in the transfer time in the CPU, DPU, and DPU transfer times, as you can see in the plot. But still, it's not flat as the kernel execution time, DPU kernel execution time. And the reason for that is that the bandwidth between CPU and DPU and between DPU and CPU doesn't scale linearly. So it increases with the number of DPUs, but it increases sublinearly. And that's what we observe in the plot here, which is not bad in reality. So if we look at for example, this DPU CPU time for a single DPU and this DPU CPU time for 4 DPUs, they are very, very similar, even though in this case we are transferring 4 times more data from the CPU to the DPUs. Okay, now we are going to talk about the comparison to CPU and GPU, and here, we have used 2 state-of-the-art devices. One of them is an Intel Xeon CPU. The other one is an NVIDIA Titan V GPU, which is a quite powerful GPU, high-end one. You can also find the CPU and GPU versions of the PIM benchmarks in our repository. They are available as well there for possible comparison. We have used here the largest data set that we can fit in the GPU memory, and this is important because we are not doing any sort of memory over subscription. And recall that the amount of memory that we have in the PIM-enabled system is much larger than the typical size of the memory, the device memory on a GPU, which is around 12 gigabytes. I think it's 12 gigabytes actually in this particular Titan V. But even the most powerful GPUs these days with the largest memory are only like 40 gigabytes. I think is the A100 GPU. That one has 40 gigabytes, which still is like 4 times smaller than what the largest admin-based system has. And in this case, as I said, we are pretty fair with respect to the DPUs because we are using the largest data sets that we can fit in the GPU memory. If we need to oversubscribe memory, probably the execution time results for the GPU would be probably worse. And in the experiment, also in the results that you are going to see as well, we are not including transfer times. So let's say neither CPU, DPU, nor DPU, CPU transfer times, but also we are not including those times for the GPU as well. But in the case of the execution, the PIM-enabled PIM system, we are including the DPU kernel time and the inter-DPU communication time. So this is important for you to take into account. And we observe out of the 16 workloads, we observe that some of them are more suitable for processing in memory, are those ones here on the left. In total, 10 of the 16 benchmarks, while for 6 of the benchmarks, we can say that they are less PIM suitable. And we are going to see why. And here on the right-hand side of the plots, you see the geomean for the more PIM suitable ones, geomean for the less PIM suitable ones, and the geomean for all of the workloads. And in the plot, we have results for CPU, GPU, and then for the 2 admin-based PIM systems. The first observation from this plot is that both PIM-based systems, APMEM-based PIM systems outperform the CPU for all benchmarks except these three, SPMB, BFS, and NW. This is not a surprise because, as we have seen in the strong experiments before, these three benchmarks suffer from load imbalance or excessive inter-GPU communication that is essentially making that the performance of these three is not so great on the APMEM-based PIM systems. Yeah, if we we check the speed up for the remaining 13 benchmarks, we see pretty nice numbers here. It's almost 2 orders of magnitude faster, the larger APMEM-based PIM system with respect to the CPU. So then when comparing to the GPU, we see that for 10 PRIM benchmarks, the larger APMEM-based PIM system outperforms the GPU, and it does it by an average of 2.54 times, which is pretty interesting speed up as well. And even for the smaller APMEM-based PIM system with only 640 DPUs, the performance of this system is within 65% the performance of the GPU for the same 10 PRIM benchmarks. So in the end, regardless of what's the number of DPUs in the system, there are some workloads that are more naturally suitable for the APMEM-based PIM system than others. And these workloads, these 10 workloads have 3 key characteristics. The first one is that they use streaming memory accesses. And the good thing of this is that when using streaming memory accesses, as you may remember from our micro benchmarking lecture, is when we can exploit so we can exploit more bandwidth between NRAM and WRAM. So we are, let's say, benefiting more from the fact that we are closer to memory and we can exploit larger bandwidth. Also, in these 10 benchmarks, there is no inter-DPU synchronization or very little inter-DPU synchronization. For example, just final result merging. And also these benchmarks have no or little use of complex operations that, as we also discussed in a past lecture, are not so good at the current ALUs, at the current pipeline of the DPUs. And so these complex operations are integer multiplication or integer division or floating point operations. So if the workloads doesn't use these operations massively, it should be pretty suitable for the APMEM-based PIM system. So these 3 key characteristics make a workload suitable or potentially suitable for the APMEM PIM architecture. We also run some experiments to measure the energy. We could only measure the energy on the smaller APMEM-based PIM system because of, let's say, some technical difficulties in the largest system. But yeah, there are some interesting observations here that are quite in line with the observations in terms of performance. What we can see is that on average, the 640 DPU system consumes 1.64 times less energy than the CPU for all PRIM benchmarks, even for those that are not so PIM suitable. For 12 of the benchmarks, the APMEM-based PIM system provides energy savings of more than 4 or 5 times over the CPU. I think that this is also quite an interesting number, quite an interesting energy savings. And in summary, the key observation here is that the APMEM-based PIM system provides large energy savings over the state-of-the-art CPU due to the higher performance, and also due to the less data movement between the memory and the processors. In the end, this is the main reason why we can expect good performance for processing in memory architectures and good energy savings, because the important reduction, a significant reduction in the amount of data movement. We also observed that the UPMEM-based PIM system provides energy savings over state-of-the-art CPU and GPU for those workloads where it outperforms the CPU and the GPU. So this is what we observed when we compare the energy savings with the performance improvement, and we correlate them. We essentially see, because of the reason that we discussed before, that the energy savings are related to the savings in execution time or the speed up. And the reason for that is, as I said, the main reason for this performance improvement and energy savings is the significant reduction in the data movement. Okay, just to conclude, let me give you some key takeaways. The first one of the key takeaways we actually discussed in a past lecture. Remember that we talked about a memory bound region and a compute bound region in the DPUs. In the memory bound region, we observe that the arithmetic throughput increases as we increase the number of tasklets that we use, and it's normally for workloads that have very low operational intensity. Remember actually that the throughput saturation point was pretty low, even for integer addition was pretty low. So because of that, we expect that most of the workloads are in the compute bound region. And this is actually what we have also observed in our experiments today. I would say that all of the kernels except the scan add kernel that I discussed are in this compute bound region, yeah, except that one that, remember, saturates at 8 tasklets and not 11 or more. Then the second key takeaway is that the most well-suited workloads for the UPMEM PIM architecture are those that have the 3 characteristics that I mentioned just a few slides ago. But one of these characteristics is that these most well-suited workloads use no arithmetic operations or only simple operations like integer addition and subtraction or bitwise operations. They don't use integer multiplication or division or floating point operations, and this is what we observe in these 10 PRIM benchmarks. And also that these 10 PRIM benchmarks require little or no communication across DPUs, the inter-DPU communication. And as the final key takeaway, just to wrap up here, remember that UPMEM-based PIM systems have shown to outperform state-of-the-art CPUs in terms of performance and energy efficiency on most of the PRIM benchmarks. We have also seen that the UPMEM-based PIM system outperformed the state-of-the-art GPUs on a majority of PRIM benchmarks, and the outlook is even more positive for future PIM systems, as we can expect. We are just analyzing the first generation of the first real-world PIM architecture, and also that we expect and observe that the workloads where the UPMEM-based PIM system is more energy efficient as compared to CPU and GPU are those workloads where the UPMEM-based PIM system also provides performance improvements over the CPU and the GPUs. And the reason for that, as I said before, is because of the significant amount of data movement reduction. Okay, and I guess that this is essentially all for today for this lecture. If you want to know more about all these experiments and much more discussion and key observations about all these strong weak scaling experiments and comparison to CPUs and GPUs, I can recommend you to take a look at our paper that is available in arXiv. And also, you know that the PRIM benchmark suite is publicly available, and you can also download and run it on your own system just by downloading the UPMEM SDK. You can, the UPMEM SDK already includes a simulator, and you can run these PRIM benchmarks on the simulator and in some way reproduce the experiments that we run on the real system. And if you have access to a real system, even better. And this is all for today. Just to give you a very brief update, a very brief advance of what we will cover in the next lecture. We will talk again about processing using memory. In this case, we will present an end-to-end framework for implementing bit serial SIMD operations in DRAM. That is called SIMD-DRAM. The presentation will be based on a paper that we published in ASPLOS this year, and I think that this is quite a fascinating topic, processing using memory, as you may remember from previous lectures. And this SIMD-DRAM is a really interesting framework that it's intended to make processing using memory more practical and more usable. But this is what we will cover next Tuesday. So this is all from my side. Let me know if there are any questions. Thank you very much for your attention. I don't see any questions in YouTube. I don't know, guys, if you have any questions here in Zoom. Let me know. If there are no questions, then I think that we are done for today, and we will continue next Tuesday.
Thank you.
Yeah, thank you.